Good afternoon. Today I will start principle of mathematical induction. Before I come into the main topic, I will discuss with you certain things like statement. How can you define a statement? Suppose that I tell you, you throw a die and 6 occurs and you report it to a certain person. It is also 6. So this is a statement. This is a true statement. Die shows 6 and you have reported 6. So this is a true statement. So now, definition of a statement. How can you define a statement? A sentence is called statement. A sentence is called statement if either it is true or false. I am writing some statement. Statement. Number 1. 3 divides 6. This is a sentence. 3 divides 6 is a sentence and it is a statement. It is true statement. Second, Shahrukh Khan is an actor. Is an actor. This is also a sentence and this sentence is a statement and it is also true statement. Now, next, third, there are 6 days in a week. As you know that this is a sentence, but this is not a statement. This is not a true statement. This is a sentence, this is a statement, but this is not true statement. Because there are 7 days in a week. Here you are given that there are 6 days in a week. So this is a statement. It is false statement. It is false statement. Now, what is mathematical statement? Mathematical statement. In the same way like sentence is a statement like that. There is also mathematical statement and that statement are true or false. So mathematical statement, I am writing some mathematical statement. Number 1, "35 is a multiple of 5. It is a true statement. Now second, 35 is a multiple of 5, it is a true statement. X plus 1 is a factor of x square minus 3x plus 2. X plus 1 is not a factor of x square minus 3x plus 2, but it is given, so it is a false statement. It is a false statement. Why this is false statement? Because x plus 1 is not a factor of given quadratic polynomial, and here given, so it is a false statement. Now third, A intersection B equal to B intersection A. Since you know that intersection is commutative, therefore it is a true statement. It is a true statement. So I have discussed, I have given example, all this proves that there are sentences, and the sentences are known as a statement. Sometimes that statement is true, sometimes it is false, but it is a statement. A statement can be a true or false, and sentences are a statement. You remember this line, and this is very important. Now, principle of mathematical induction. Now we come to principle of mathematical induction. Principle of mathematical induction. Now, motivation is tending to initiate an action. Motivation is tending to initiate an action. This line is very important for you to learn principle of mathematical induction. Motivation is tending to initiate an action. This line is very important. Here basic step motivates us. Basic steps motivate us for the mathematical induction. For the mathematical induction. This is also important line to understand principle of mathematical induction. I have written two sentences. Motivation is tending to initiate an action. Here basic step motivates us for the mathematical induction. So now come to principle of mathematical induction. Principle of mathematical induction. In this, we are going to check whether the given mathematical statement is true for all the natural numbers or not. So now you see that let Pn be a statement having n natural numbers. N natural numbers such that number 1, this is called basic steps. Basic step. In basic step, we are showing that P1 is true. P1 is true is also known as Pn is true for n equals to 1. This is the basic step in which you are showing that the given statement is true for n equals to 1. Second, induction step. If Pk is true, this is your assumption. You assume here in this induction step, you assume here your given statement is true for n equals to k, then it is also true for n equals to k plus 1. We say that the statement Pn is true for all natural number n. All natural number n. For all natural number n. For all natural number n can be written as for all, this read as for all. This is the symbol. This is the symbol which we read as for all. For all n belongs to n. For all natural number n can be written as in this way also. So this is the principle of mathematical induction, in which let Pn be a statement having n natural numbers such that your basic step P1 is true, that is Pn is true for n equals to 1. You can write in both the way, and induction step is if Pk is true, then it is also true for n equals to k plus 1. We say that this statement Pn is true for all natural number n. So now you see, next thing, working step for any question. In order to prove a given question is true for all the natural numbers, what are the working steps? What you supposed to do in that? So you remember this thing. Step 1, working step. Step 1, we show that the statement Pn is true for n equals to 1. Step 2, we assume that Pn is true for n equals to k. In step 3, we will prove that pk plus 1 is also true. If Pn is true for n equals to k in step 2. So there are 3 steps in which we are showing any given statement as a question that will be true for all the natural numbers n. Now coming to question, let Pn be a statement. Question 1. Let Pn be a statement. Let Pn be a statement n into n plus 1 into n plus 2. This is the statement. Is divisible by 12. N plus 1, n plus 2, n plus 1, n plus 2 is divisible by 2. 12. Divisible by 12. This is a statement so that P3 and P4 are true. P3 and P4 are true, but not P5. Not P5. So how will you write the solution for this? Your solution is, let a statement is denoted by Pn. Is denoted by Pn. So Pn can be written as n into n plus 1, n plus 2. You find the value of P3. Put n equals to 3. P3 is equals to 3 into 4 into 5. That is equals to 60, which is divisible by 12. By 12. Therefore, P3 is true. Similarly, you find P4. Your P4, put n equals to 4. Your P4 equals to 4 into 5 into 6. 6 5 is 30. 34 is 120, which is divisible by 12. Therefore, P4 is true. So now let n equals to 5. You can write your P5 as 5 into 6 into 7, that is equal to 5 into 42, 210, and it is not which is not divisible by 12. Divisible by 12. Therefore, P5 is not true. So, in this way, you have shown here the given statement Pn is true for n equals to 3 and n equals to 4, but not n equals to 5. Now, next question. Prove the following by using the principle of mathematical induction that it is true for all the natural numbers. Question 1. Prove by using principle of mathematical induction that the following statement is true. Statement is true for each n belongs to n, for all n belongs to n. This symbol read as for all. One square plus 2 square plus 3 square plus and so on plus n square is equals to 1 upon 6 n into n plus 1 2n plus 1. This is a mathematical statement in which we have given that sum of the square of first n natural number is this much, and your this sum of n natural number is true for all the natural number. So now let this statement is Pn. Let the given statement is Pn. So you can write Pn equals to this thing. There are now here becomes three terms. One is Pn, another is this series, and then that sum. There are three terms, three components of this statement. Pn denotes the sum of n natural numbers. Now you come to the solution. Let n equals to 1. This is the basic step. You are proving your this statement is true for n equals to 1, and this is called basic step. So when you take n equals to 1, your P1 denotes the sum of 1 terms of the series. Sum of 1 terms of the series. So 1 term is 1 square, and that is equal to, when you substitute on the right hand side, you will get 1 by 6 into 1 into 2 into 3. So it is 6 by 6. So your P1 denotes 1 equals to 1, which is true. Therefore, Pn is true for n equals to 1. And now after that you are going to induction step. In induction step, what you are doing, first of all you you are assuming that the given statement is true for n equals to k, and then you are going to prove it is also true for n equals to k plus 1. So we assume that this is induction step. We assume that Pn is true for n equals to k. So you can write your pk means sum of k terms equal to 1 square plus 2 square plus 3 square plus and so on. Kth term is k square, because here nth term is denoted by an is n square, then kth term becomes k square, that is equal to 1 by 6 k plus 1, 2k plus 1, this is 1. Now we are going to prove, now we shall prove that Pn is true for n equals to k plus 1. One thing is very important to understand while doing this kind of questions. So you see that, can I write sum of 3 terms equal to sum of 2 terms plus third term? What is this? This statement implies that sum of 3 terms, equal to sum of 2 terms plus third term. When you continue this procedure, similarly sum of 4 terms can be written as sum of 3 terms plus 4th term. P4 means P4 denotes sum of 4 terms equal to sum of 3 terms plus 4th term. A4 is 4th term. Sum of 4 terms equals to sum of 3 terms plus 4th term. So when you continue, then you can write your pk plus 1, sum of k plus 1 terms equal to sum of k terms plus k plus 1th term. This statement implies that sum of k plus 1 terms, is equal to sum of k terms plus k plus 1th term. You remember that. So you can continue this procedure in this way. So here you have assumed that pk is true, your given statement is true for n equals to k, and you will prove that you are going to prove it is also true for n equals to k plus 1. By all this discussion, we reach to the conclusion that you can write your pk plus 1 is equal to pk plus ak plus 1. So question is that how you will find pk. Pk, you have already assumed that your statement is true for n equals to k. So your pk is this much. Your pk equals to 1 by 6 k plus 1 into 2k plus 1. This is sum of k terms. You assume that is true, and it is given in 1. This is 2. So your pk is this much. How will you find AK plus 1? So now you search for nth term from the series. Nth term of the series is given in the question. So your nth term an, nth term equal to an equal to n square. So you can write your ak plus 1 equal to k plus 1 whole square. Now you have pk means sum of k terms and k plus 1th term. Substitute pk and ak plus 1 from 2 and 3 in 4 we get substitute pk and ak plus 1 from 3 and 4. From 3 and 4 in 2, because pk is given in 2 or 3, pk is given in 3 and ak plus 1 is given in 4. So substitute pk and ak plus 1 from 3 and 4 in 2, we get pk plus 1 equal to 1 by 6 k plus 1 2k plus 1 plus ak value of ak plus 1, that is k plus 1 whole square. Now after this you follow this step. pk plus 1 equal to, you have to simplify this algebraic polynomial. So you find out the common terms in both the term. K plus 1 and k plus 1 is present in both the terms, so it is common. Take out that k plus 1 in bracket k into 2k plus 1 upon 6 plus k plus 1. When you find the LCM, your LCM is 6. Here 2k square plus k plus 6k plus 6. Very easy simplification. Now you can write this is equal to k plus 1 2k square plus 7k plus 6 by 6. You factorize this polynomial. Find the factor of 2k square plus 7k plus 6. So as you study the factorization by splitting middle terms, that goes like this: 2k square plus 7k plus 6. So what you are doing? You are taking the multiplication of 2 and 6. Multiplication of 2 and 6 is equal to 12. Find the factor or prime factor of 12 in such a way that their product is plus 12 and sum of the prime factor of 12 is 7. This 7, that is the coefficient of k. So in this way 12 can be written as 4 into 3. 4 into 3 is 12 and their sum 4 plus 3 is equal to 7. 4 into 3 is 12, that is equal to 2 into 6, and 4 plus 3 is equal to 7, that is the coefficient of k. So in this way you can write 2k square plus 7k plus 6 equal to 2k square plus 4k plus 3k plus 6 in this way. So by applying a splitting bundle term, you can factorize this expression k plus 1 by 6 in the bracket 2k square plus 4k plus 3k plus 6. This is equal to k plus 1 by 6 in bracket 2k inside k plus 2 plus 3 inside the bracket k plus 2. Now again k plus 2 is present in both the terms, that is taken out k plus 1 k plus 2 by 6 in bracket it is 2k plus 3. So this can be written as this is equal to 1 by 6 k plus 1 k plus 2 into 2k plus 3. So how can you verify that this pk plus 1 is true? Now you come to the statement Pn. In Pn, this is your Pn. In this step, when you take n equals to k plus 1, if you take n equals to k plus 1 in this step, then what happens? Your pk plus 1 equal to 1 by 6, n is k plus 1, this factor becomes k plus 2, when you substitute here, that will becomes 2k plus 3. So you can write, therefore Pn is true, or which is true. So now you can say that Pn is true for all the natural numbers. Hence, Pn is true for n equals to k plus 1. Thus, Pn is true for all n belongs to n. So this is your one of the question. You practice this. Now I am coming to